Okay, I think we are recording. Yeah. Shiv Agarwal, do you have a question? Then please unmute. Otherwise, you can mute yourself. Is that fine? Shiv Agarwal, are you able to hear me?
Yeah, yeah.
Yeah. Please mute yourself. There's a background noise coming in. Fine. Yeah, so we'll start the today's session, live session. Week two of your course Intro to Machine Learning. And today I was thinking to do these three topics. I mean, generally main one topic which is the decision trees. I saw that a lot of you had questions on the forum. Let's do step by step. If taking an example, what exactly comes to be the entropy values and the gain values and etc. And then we'll discuss a bit on the Kaggle so that it's easy for you to get started if you want to for with any data set and any algorithm that you want to try. And then we can cover up other doubts that you guys might have for for the coming week assignment and so on. Yeah. Um, all right. So we'll start with this idea of decision trees. Um, Anyone want to tell me what decision trees is quickly? Like, what do we do here, and what is the idea behind decision trees? Anyone want to just summarize it for me? Any thoughts?
So is it like regarding like whether to play tennis or not? Regarding the temperatures, humidity, and wind, whatever the conditions you have. With the
Right.
help of that, whether to play tennis or not. Yeah.
Right. And so I can solve that in multiple ways, right? I can also use linear regression. So what do we do in decision trees specially? Like what gives it the name decision tree, by the way?
Taking like decisions. So basically, uh, taking the like considering whatever the parameters given, so you can bifurcate and then decide whether it will be easy rather than.
Right. Huh. So yeah, so we want to take decisions on, for example, let's say some output variable or some classification problem. And the idea here is instead of building a linear model, what we are trying to do is we are trying to use like a tree structure based approach, right? So where we are trying to see, we try to build a tree, and the tree is basically uh, a data structure in which we have like a root node, and then we have children for the particular root node and so on and so forth, right? So here what we want to do is we want to take decisions on a particular variable using features, but in a tree manner. So we take we look at one particular feature at once, and then take multiple decisions throughout the tree. So that's the idea. Now here, for example, for this particular example, here what we're trying to do is we have these features that are there here, right? And mm, yeah, features, and this is the output, or basically your decision variable in some sense, right? So you want to decide whether should somebody play tennis or not based upon these four let's say weather features on the particular day, right? So now the idea is that if I want to build the best decision tree, that can be a NP-hard problem. Now so then what we do is we take a greedy approach. We say that okay, we'll try to build the least depth tree in some sense, And for that, what we do is one measure of growing a particular tree from a from a root node and so on is using this idea of entropy and the gain in entropy. Now, anyone want to tell me what entropy is for this particular data set as such? Any thoughts? So here the variable of interest or the output in some sense, right, is tennis, right? And this can take two values, that is yes or no, right? So should you play tennis or not play tennis? Now we want to know the entropy of the data set that I have here. Let's say I'll call this set as D. So entropy of the data set D is what in terms of this tennis variable? How do we calculate something like this?
Yeah, that is a formula like minus E summation of P log Pi n
Minus,
to 1 to n minus summation of n is equal to 1 to whatever n numbers, number of rows, and P log P log Pi, yeah, Pi log Pi, or n, yeah. If you're saying yeah, E means n, yeah, Pn log Pn,
okay.
and
So
some that is some, yeah, summation of all
Pn log P.
probability, yeah, the probability of each thing. P is the
Right. So
probability.
sorry,
P is the probability of each whatever features.
P is probability of what?
Probability of like features, or like example, if you say outlook, P is the probability of sunny, almost sunny, overcast, plan, something like that. That's how it is.
Okay. So here n is what, by the way? Number of data
Number
points, is
of
it?
rows, like how many rows are there in that the data set. Like
Okay.
here it is like 14, so n is 14 here.
Okay. Number of rows. Fine. So then you're saying that I can use Pn log Pn. Okay.
Yeah.
So
So for each data set, find out, then do summation for all the other whatever the features, number of features, complete features. Like
right. So now here, what is Pn though? So okay. So for every row, I'll have a value, no? So what is Pn for
yeah.
this particular row?
No, not like row. I think it's probability of each features column, right? If I'm like
Each.
example, well, we should find, yeah, probability of outlook, temperature, probability of humidity, probability of wind, whatever. So that's how it is, right?
I think only the output classes, number of classes we have S or no, right?
Right.
So totally we have 14 features. So how many yes we have and how many no we have. So based on that we should go. I think so.
Right.
Yeah,
So
like 1, 2, 3, 4, 5, 6, 7, 8, 8,
hmm.
No, no,
8 and
nine
6.
and nine
9,
and
8,
five.
8.
9 and 5.
1, 2, 3, 4, 5, 6. It's moving. 7, 8, 9. Yeah, 9. 9
Yeah.
and 5. 9 and 5.
3, 4, 5. Yeah. So
9 yes, 5 4. You know,
5
nose.
no's and 9 yeses. Right?
Yeah.
Okay. Huh. So now, okay. So then what is the entropy of the tennis variable then?
It's 9 by 14. Something the log of minus 9 by 14 log of 9 by 14. Then plus I mean like yeah, minus bracket like minus 5 by 14 by log 5 by 14.
Right. That's it.
The
Right.
bracket should be there. I mean like, yeah,
Right.
the whole I
Correct.
mean the whole thing should be in bracket. I mean
Yeah. I mean, that's fine.
correct. Yeah.
Right. Okay.
Yes.
So here, if you see, so this is the entropy variable, entropy for tennis variable, right?
Hmm.
So what we do is basically we look at all possible classes. So if you have entropy of any, let's
So I
say,
have a doubt. Is it like logarithm to base, because normally SI is logarithm of 2, but how is it like, how do I decide like which logarithm to use, like 2 base 10 or base E? There are two, so they say 2, right? Log 2.
no, it's ideally supposed to be log base E.
E.
E,
Okay.
E is a general, this one that you can take. But the point
Because
is,
someone in the Google I saw it's 2. So I was like confused.
right. But the point here is, because all of these logarithms are scales of each other, right? So I can always write log 2 of x, let's say, is log e of x with some factor here. I think log e base 2, something like this, right? So this factor is constant, right? So in your algorithm decision making, it doesn't matter you take log base 2, base e, all of that doesn't matter, right? Is that clear? So it's just that the way you define the units will differ. So when you say, let's say log uh, base 2 of 4, so this unit is supposed to be 2 bits. So we're saying I need 2 bits to represent 4, right? Um, 4 possible combinations. And let's say if I take, let's say log e square of e, let's say, right? This is again 2, but this is measured in the units called nats. So nat and bit, they're all just basically scales of each other, like how kilogram and gram are just scales of each other. So any of these you can use at the end of the day. You can use log base 2, log base e. That doesn't matter. At the end of the day, when you're taking the what you can say, the decision to which node to choose or which feature to choose to split on, because everything is in scales of each other, you can choose one convention and move ahead. It will not change your what attribute you choose to split, etc. Only the value will change, which is fine as long as you're consistent across your whole algorithm procedure. That is fine. That's not a problem. Is that clear? Okay. So here, let's say, so we generally define entropy, right? So entropy, let's say H, generally we use H for any entropy convention. Let's say of a random variable X is defined as this quantity, that is expectation of log of P of X, whatever its probability is over all possible values that X can take. So negative of this, right? So then here, because what all values can tennis take, that's the question we're trying to answer, trying to understand, right? So what all values can tennis take? Tennis can take only yes and no, right? So then we see, okay, what is the probability? And when you expand this for, let's say, discrete variables, what it turns out to be is just basically summation over, let's say, P of X log P of X over all possible values for X, right? So here, tennis can take only no or yes. And then here you get, for example, so 9 by 14. So what's the probability for it being yes? What's the probability of it being no? You take those two probabilities and you can calculate it in this format, right? So now this value is going to come down to be Sarika. So if you use log or log to answer that, so what to select? Okay, so let me just confirm this particular thing then. Oh, there was entropies and all, is it? Fine. Just a moment. Then let me confirm it right away. Mm. Okay, so we're using convention of log base 2. So everyone just please use log base 2. Yeah. In your calculations or whatever it is, right? So the PDF uses log base 2. So we'll use log base 2 and go ahead. Is that clear, Sarika, then? Okay. So now, what happens is, so this becomes, so you will calculate this value, right, at the end of the day. So this becomes some, you can, work out the math, you'll get some value, let's say some A value, right? Now, so this is how you calculate entropy of any random variable, right? Of any feature. For example, if I want to ask you, what is the entropy of, let's say, Outlook? So we're just doing the entropy calculations. I'm not at all discussing about the choosing the root node, anything as of right now. Okay, so what is the entropy of outlook variable? Any thoughts? How would you calculate this?
Find three fractions and then add some over three fractions, say minus f1 is f1.
Right. So you'll have three fractions because outlook can take three variables or three values, right? Sunny, overcast, and rain. Okay. So sunny, we have how many? 1, 2, 3, 4, and 5. So 5 by 14, log 5 by 14 minus, right? And then overcast is 1, 2, 3, 4. So 4 by 14 log 4 by 14. So 5 plus 4, 9, and it should be 5. So rain 1, 2, 3, 4, and 5, right? So minus 5 by 14 log 5 by 14, right? This becomes the entropy of outlook variable. Is this clear? Any doubts on entropy calculation? No? Fine. So we'll move ahead. Um, so then the next thing I wanted to discuss is how to select the root node, right? Now I have, I had, let's say, so many variables with me, all these four features that I had with me. So how do I now choose which node to start from, right? Where do I start the decision tree from, right? So for that, what we do is we use this idea of information gain or entropy information gain, basically, right? Information gain. And what we do here is, let's say I have a node um, uh, of for some feature, let's say n. Now this n can be any of these features, that is outlook, temperature, humidity, or wind, right? So now for each of these possible values, I can have multiple children, right? So what I do is I look at the entropy of the tennis variable uh, at this node, right? Then subtract from that the average entropy of the children, right? And here the child of a node or the children of a node, at least in this particular algorithm, the ID3 algorithm that we are discussing. So children of a node are basically all possible values that the node can take, right? So here, if I were to select, let's say, Outlook as my, in my possible values for this particular first node, so then I would have, um, let's say, so Outlook, right? And this can take three values, that is sunny, overcast, and rain, right? And actually, let's keep it a bit different. So yeah, sunny, outlook, and rain. And this is then the next set of nodes that I have got, right? So this is the parent node and this is always children node, right? So then, so for a particular node, when I'm trying to, look for this, what feature to select, I look at the information gain that I would get if I were to split on this particular feature, right? So for that, what we do is we look at the entropy in this particular node, right? And then subtract the average entropy of the children. Now, entropy of this of the root node is always the same, right? Because I always have these first set of variables that I have here, right? I have these what 9 yes and 5 no's of tennis, right? So 9 yes and 5 no's of this tennis variable. So I have 9 positive examples and let's say 5 negative examples. Now, after I split on all the outlook equal to sunny, right? Then how many positives and negative examples are left in this particular node? That is what we want to know. So for sunny, if you see, I have 1, 2, then I have 3 and 2. So I have 2 positives and 3 negatives in this particular node. When I have overcast, it's always yes, right? So it's always just how many? I have 4 yeses, right? Saikat, yes, you will get the recordings. I also mentioned the link in the discussion forum, so you can just check that. So I'll upload it by today or tomorrow. And then the rain example, rain feature. So I have 2 yeses, 3 yeses, and 2 nos, right? 3 yeses and 2 nos, right? Do I have so 5 plus 5, 10 plus 4, 14? Yeah, correct. Right. So now what we do is I look at the entropy of this node. Entropy of this node we have already calculated, right? The previous value that we got here. Here, right? This A value, whatever we had. So that I know already, right? The A value. And then average entropy. So for this, first we want to look at the entropy of this particular node. So how will we calculate the entropy here? Again, same thought process. I have 5 total values. Among them, 2 are positive and 3 are negative. Same thought process we will use. And here again, we are calculating the entropy of the tennis variable. That is our decision variable always, right? So don't get confused thinking of outlook. When I'm choosing outlook, I will use the outlook variables entropy. No, we're always looking at the tennis variables entropy. We want to reduce or we want to gain as much information as possible about the outcome that we want to predict. We don't really care about what is happening in the entropies of these guys. Rather, it's about the the output variable that we want to know about, right? So so the entropy for in this particular node, which has 2 positives and 3 negatives, would be, anyone want to take a gander? What will be the entropy for this node?
It's 0.94, I guess.
I'm sorry.
0.94.
No, yeah, I guess that's fine, but I'm just asking about the formula. I'm not calculating it. Yeah. So what the formula would be?
It will be
How would you
minus
calculate?
It's
5
2 by 5 log 2 by 5.
minus 2 by 5 log 2 by 5
Minus 2 by 5 log 2 by 5
plus
and
minus 3 by 5
minus 5 by 14.
3 by 5.
3 by 5 log
3 by
3 by 5.
right. Okay. So here the idea is in this node, see, somebody said 5 by 14. So that was for this outlook variable here in the parent node, right? So here we are looking at the only for this particular node. Now in this node, I only have two samples of this tennis variable where it is yes, and 3 samples of tennis variable where the tennis variable is no. So only for this particular set I want the entropy. So therefore, I will look at these particular proportions, not the overall proportions. Okay. All right. Now, what is the here the entropy of this for this node? The,
0.
okay. Why? I mean,
There is no
let's say
answer. It's all positives.
it's all positives, correct? fine. I mean, mathematically, if you wanted to, if I see, I gave you a formula for entropy, right? Can you, I mean, if you use that, do we get 0 as the entropy?
Minus 4 by 4 log of 4 by 4.
Right? So this would turn out to be
0.
right, because it's just minus log 1. Log 1 is 0, so this is 0. So no entropy here, right? Okay, yeah. And then same thing here we will do for the, let's say the rain example of the outlook. And this will just be same as this guy, right? Minus 3 by 5 log 3 by 5 plus minus 2 by 5 log 2 by 5. So whatever value you get here, let's say some value m, you'll get the same value here, right? Now, when you're taking the average here, we will not take the a normal average. We'll take a weighted average, right? The reasoning being that we have a more number of samples here compared to this particular node. So obviously the weightage that this particular node gets should obviously be higher, right? So then what we do is, let's say I got this value a here, right? So the information gain. So the information gain, if I use, let's say, Outlook as my root node, right, would be entropy of the tennis variable without any, this one, minus the average of these guys. So now what I will do here is this becomes, let's say a, we had the value a here, right? A minus the average. So here I have 5 examples out of 14. So its weightage is 5 by 14. So 5 by 14 of, let's say, this m, right? Plus 4 by 14 of 0 plus this 5 by 14 of, yes, a minus the average, correct, of m, right? So whatever value you get here, I mean, this will be the information gain, right? Now the same procedure you have to repeat for if I were to take, let's say, temperature as my root node, then how much information gain do I get? If I were to take humidity as my root node, if I were to take wind as my root node, right? That is the calculations that you need for doing the information gain, right? So any doubts in this part as of now? Is it clear? Okay. Okay, fine. Good enough. So now, yeah. So let's say if I have, the same data set, but with the small, let's say, twist. Can take one more example. So what do you mean by one more example? Do you want another, part of the, next level of node split, or different example?
Let's split again
I'm sorry.
against the sun. Can we split again against the sun where it's 2, 3?
I'm sorry, 2, 3 of what?
Yeah. From outlook, sun is 2, 3. From that tree, yes. The left, that sun is 2, 3. Can we split again? Which attribute can we use?
Yeah. Okay. Fine. Okay. Yeah. So yeah, let's do that. Right. We'll take one more, step down. Right. So let's say, we ended up choosing Outlook for whatever reason. We say that, okay, that we got the highest information gain there. So what we'll do is we will say now I have Outlook as my root node. This is fixed. I don't touch this anymore. And I have Sunny. I have, what is this called? Overcast, and I have the rain, right? Now, here I had how many? Here I had 9 positives and 5 negatives, let's say. Same here, 4 positives. And this was what? 2 positive, 3 negative. Yeah, so 2 positive, 3 negative. right? Okay, so now I have to choose one more, so I have to take one decision, that is which feature to select now. So the outlook feature is anyway used up, right? There is no change in, there's no difference in the outlook variable in this particular node anymore. All of the variables in this, all of the data points in this particular node have the outlook variable equal to sunny. So there's no entropy there in the first place. So now the possible choices are either temperature, humidity, or the wind. Correct? So now what do I do is I look at, let's say if I want to check whether does temperature is temperature the best value to choose. So how do I go about doing it? I say that this particular node I will now split on temperature. Temperature is how many values can take? Only hot. Oh, it can take 3 again. Hot, mild, and cool. Is it fine? So hot, let's say mild and cool, right? So now we have to look at only for outlook equal to sunny. Only for those rows we have to select, because these the examples here have only outlook equal to sunny. So all of these are gone. We don't care about any of these examples. All right. So this is also gone, and this whole set is gone. Right now, among these sets, now I look at, okay, how many, so I have hot, I have mild, I have cool. So how many, examples of tennis are equal to hot, right? So here I have 1, 2 no's, and oh, this is also gone, is it? So only 2 no's, right? So 2 minus, that's all I have. Then for temperature equal to mild, again I have only 1 no, I think, yeah. And temperature equal to cool, I have only one positive, I mean one yes, right? So if you see here, the entropy of this guy, entropy of the tennis variable for all these variables is, can you tell me what the entropy is?
All are zero.
All are zero, right? Because there is no, oh, mild is, I have 2 milds, is it? Oh, good. Okay, thanks. So 1 yes and 1 no. That's good. So okay, let me just correct that. Where is it? So 1 positive and 1 negative. So 1, 2, 3, 4, 5. Yeah, correct. Okay. So yeah, so let's do that. Let's do the math then. So the hot is 0, right? Why? Again, same, minus 2 by 2 log 2 by 2, right? This is 1, so log becomes 0. Same thing for the cool one, right? I have 1 by 1 log 1 by 1, again 0. This is interesting, right? So here I have minus 1 by 2 log 1 by 2, right? Plus minus 1 by 2 log 1 by 2, right? This is the entropy of the tennis variable when I have outlook equal to sunny and temperature equal to mild. Okay, so this will turn out to be, let's say, some value, some p, right? Oh, let's not use p. Some value q, right? So now what I need is I want to find the information gain. That's the final goal. So the information gain when I choose temperature, right, as my feature to split on this particular node will be equal to the entropy of this particular node, right? That is outlook equal to sunny node, right? Outlook equal to sunny node minus the average of its children. The children are these hot, mild, cold, right? Average of the children. So outlook, see, the entropy of outlook equal to sunny, we have already calculated, right? In the previous slide, if you see. So we already have this M, right? This is exactly what we need to get to subtract in the first term. So that is exactly here. This is M only, right? Minus. Now, what is the average of children? So if you see here, again, we have to take a weighted average. So it's 2 by, how many are there? 5 examples, total 5 examples in this node. So 2 by 5 into 0, right? Then plus again 2 by 5 into the entropy is Q here, right? And then again plus 2, sorry, 1 by 5, right? Plus 1 by 5 into 0, right? So you'll get something m minus 2 by 5q or whatever. And then that will be your information gain. If I choose temperature as my feature to split on this, but on this node, then you have to do the same procedure. But if I choose humidity, then if I choose wind, and then compare all of these, whichever gives the highest information gain, that you will choose to split. Yeah. Does that clear your question? Pardon?
Yes. Thank you very much.
Okay, good enough. Right. So, okay, any other doubts? Any other thoughts?
Sir,
Questions?
sir, for the temperature mild, we have Q here. So will Q be 1? Because both classes are equally probable and the entropy is highest in keeping that condition. Will
Okay.
Q be 1?
0.5. 0.5.
So you can see here, it'll be half log 2 plus half log 2, right? It'll be just log 2, base 2. When you use base 2, so it'll be 1. That's it. You're right. I hope this step is clear. From this step to this step is clear.
Yes, sir.
Okay.
Actually, hot 2 plus 2 minus, right?
No. Why 2 plus 2 minus?
2 no, 2 yes.
No. But see, hence I said, so we are looking only for the rows where outlook equal to sunny, right? Now I have these two rows where outlook equal to sunny, these two rows, and this row. That's it. I have 5 rows. Now in these 5 rows, how many are hot, so for hot, how many are then yes or no? That's you want to calculate. So if you see, in these rows, I have two temperature equal to hot is only for these two particular rows. It's mild, cool, and mild here. Now, therefore, in these two rows, all the values are no. Hence, P like 2 minus. Yeah. Okay. Any other doubts? So, shall we do one more layer? Then shall we look at, let's say, this R or what rain value? Otherwise, if you're fine, then we'll move on to the next topic.
I think we'll do one more. Rain value will be fine.
Rain value, fine. Let's do the rain value also. Good. So let's take. Okay. So let's see our tree again. So I had who has their mic unmuted? You can close if you don't have a question. So yeah, so let's say Outlook, right? And I had sunny here and rain here, right? Now, same question we're asking. In rain, we had how many? 2 plus and 3 minus, right? 3 plus 2 minus, sorry. Yeah. So 3 plus and 2 minus were here, right? Now, same thing, we'll repeat the procedure here. So for outlook equal to rain. So for now, so basically now we'll look at only those rows where outlook equals to rain. So therefore, all these first 3 rows are gone, right? Now, then I have 1, 2, 3. Okay, all these rows are gone, right? And then all of these rows also gone, right? All is not required. Now let's look at, for example, let's say let's try humidity here first, right? Just for fun's sake. So I need to try all of them. I need to try humidity, temperature, and wind. Let's work out the example for humidity. If I choose humidity, how many values can humidity take? It can take high and normal. That's it, right? High and normal. So I have only 2 possible children. So humidity is high or normal. Oh, we're doing for humidity, by the way. Yeah, this is later on. So we're doing for humidity right now. So now let's look at how many the distribution of this tennis variable for these two particular things. So for high, I have one yes here and one no, right? So one plus and one minus. Okay, this is the distribution here. And then for normal, I have one yes, two s. So two yeses and one minus, right? And just let's check the values: 2 plus 1 3, 1 plus 1 2, and fine. So we're done here. So now same procedure again we will do. What is the entropy of this of tennis variable in this particular node? Anyone wants to take a gander? What is the value? What's the formula and then the value? Yeah, one is correct. So same like last time, right? Same procedure as the value we did for mild. Same we're seeing 1 plus 1 minus, right? So this will be minus 1 by 2 log 1 by 2 plus again minus 1 by 2 log 1 by 2, right? Because I have one positive, one negative, total is 2. So this is for the positive, this is for the negative, right? And this, as we saw just now, it's 1. And 2 plus and 1 negative. What would the value, the formula come out to be here? Anyone wants to take a guess? This should be straightforward, no? We have done so many examples now. Anyone wants to give
Yes.
me
Minus 2 over 3 log 2 over 3
log 2 over 3
minus 1 over 3 log 1 over 3.
log 1 over 3. That's it. Straightforward, right? So just take the proportion, multiply with the log. Don't forget the minus sign, right? So this will get, let's say, some n, let's say, right? So now so now we want to find the information gain. That's our end goal, right? So the information gain will be the entropy of this node that we have, right? The outlook equal to rain node, right? That we calculated long time back, right? We calculated somewhere here, I guess. Yeah, some m we got, right? Some m we got. So that m, that's the parent entropy, right? Minus the average entropy of the children. So average entropy here, high here again has two samples out of all the five, right? So it's 2 by 5. That's the weightage of the entropy into its entropy, that is 1 plus 3 by 5 for the normal, right? 3 by 5 into this n. Whatever number you get here, this will be the information gain, right? Some number you will get. Now then what you will do, you will again repeat the same procedure for when I take temperature, when I take wind, right? And then among these three you will choose the one which has the highest information gain. Okay, is this clear? Hopefully this should give you a sense of how to calculate entropies, how to calculate let's say for example the information gain, and then how to choose a feature to split upon. Any other doubts, any other questions on this?
Is Gini index simpler than this, or is it more advantageous than information gain?
Yeah, so at least as far as I know, there is no, I mean, when you use information gain, Gini index, almost both of them perform very similarly. It is just that the thought process behind them is a bit different, but at the end you will get the similarity. Gini
Okay. Results will be same.
Almost same, almost like many people have tried both versions and seen that the decision tree that comes out to be at the end is very similar, not much changes. So you can choose any one of them, and I guess that's why ma'am also has chosen like to give one example, and Gini index is just mentioned in passing.
Okay, thanks.
Yeah.
Okay.
Okay.
Yeah. Sorry. Hello.
Yeah. Go ahead. Yeah.
Yes. My question is What if we have, for example, the root on a rain from Outlook? If we have 3 positive and 3 negative,
Okay.
okay, then we want to split on an attribute, say wind.
Okay.
Let's say wind is the high is 1, 2, 1 positive and 2 negative.
Okay. Actually, let me just draw, no? Let's see what you're saying. So Outlook, let's say you're saying that I will, look at the rain, and you're
Yes,
saying that it is positive and 3 negative. Yeah.
yes.
Okay.
Then it's wind high.
Wind high. Okay.
It has 1 positive and 2 negative.
2 negative. Okay.
Then low, it was 2 negative and 1 positive.
Two. But how will you have 2 negative here? Because the total number of rows are 3 negative, no?
Oh, okay, yes. So one. Sorry.
2 positive, 1 negative. Is that right?
Yes. So yes. This is what. Yeah. That's what I want.
Okay.
So in this case,
yeah,
the information gain will be the similar.
Will be similar in the sense similar to what?
So if I want to. Okay. So yeah, I get it. No, that's fine. It's okay. Okay.
Yeah, so I think the confusion, I mean, let's just take, just in case others also have this confusion. So the point is, see, this entropy and this entropy, you will get the same value at the end of the day, which is fine. And this also you will get, equal to 1, I guess, because both are equal here, right? And that is fine. So you can have the same entropy values and all, okay. But at the end, what are you comparing? You're comparing the information gain between different features. So wind would be one feature that you have. You will construct this, you will do the same process, 3 plus 3 minus for another variable, let's say temperature, right? And you will say, okay, temperature, hot, mild, whatever. And then you will compute its children's entropies, take the average, subtract from this entropy and all of that. Then you will compare wind and temperature. That's the comparison that we want to make, right? We're choosing a feature. We're choosing which feature should I split my node on. And that is done using the information gain on that node using that feature. That's the end. I mean, the whole decision in one sentence.
I get it. So yeah. Sorry, my question was, what if we have features which have the same information gain? Can that happen?
Yeah, it can happen. So we can take wind. So you're saying that the information gain when I obtain of wind is, for example, equal to the information gain when I choose temperature, right? So then you can take dealer's choice. I mean, you can choose whichever variable and move ahead. See, because again, see, the idea is what? The idea is you want to get to the shortest tree as fast as possible, right? And because we're taking greedy decisions at each particular node, right? So hence, it doesn't matter if I use wind or temperature. So anyone you can choose and move ahead. That's the idea behind this one.
Okay, thanks. Okay.
Yeah. Okay. Fine. Any other questions? Can you explain the least minimum slope
Actually,
method?
to select the root node,
Yeah.
We have to find out which information gain is greater.
Correct.
Right? Okay. And after selecting that outlook, then for sunny, we are going to look at the temperature, humidity, wind.
Right.
Then again for overcast, we have to do the same.
Correct.
And rain also.
Yes.
And then how we will stop the tree? When will we stop?
Okay, good question. So when do you stop the tree? What approaches has been discussed in the um, the videos? When do you stop?
Actually, as per the video, we have to stop the tree once the entropy is zero.
Entropy is zero. Fine.
Another one, then equally distributed. I think.
equal distributed, will do you want to would you want to stop there if they're equally distributed, the values?
There is no further distribution. That is, for example, all are in hot, for example, in temperature, all are hot or all are mild. Then if that is the case, we can stop, right?
Right, correct. So there is no more features left, right?
Features left.
Features, no features left, or even among the features which are left, all the values are same. So you will just have the same, node again. There's no information gain. You will not get any information gain by choosing a feature, right? So even among the ones which are left, all are same, right? So then also you can stop, right? Okay, so this is, for example, you can these are two possible scenarios. What are other scenarios that we have discussed? Do you have you seen something called pruning?
Pruning.
Right. So in pruning, what are the approaches to stop?
Pre-pruning and post-pruning.
Right. Okay. So while growing the tree, if you take decisions to stop, what is that called? Is it pre-pruning or post-pruning?
Actually, now after constructing the tree, when we stop, it is post-pruning. Am I right? Post-pruning.
Pre.
Because
Pre.
so because what
when information is not above or threshold, it's called dividing the things.
Right. So the idea is that if you grow the tree until the end, right? So we haven't yet grown, right? We have just looked at, let's say, two variables here, right, till now. So if you grow the tree until the end, until we reach these conditions, entropy equal to 0 or no features left or whatever, right? If we do that and then we say, okay, now I will try to cut down some nodes or whatever, that is called post pruning. Now, in let's say in pre-pruning or whatever, in that case, when do you stop growing the tree? Anything that rings a bell from the classes? So the very standard sort of approaches present here when you want to pre-prune. Uh, so yeah. So let's say, for example, the number of examples that I have, right? Number of examples in that particular node are less than some threshold. Sorry, please mute yourself. Then what we will do, we will not expand this rain node at all, right? Because the number of hello. Yeah, I guess. Sorry. Yeah. So can you hear me now?
Yeah.
Okay, good. Yeah. So one example that we one particular idea is the number of examples in a particular node, right?
8,000 8,000
hello, Malan, can you mute yourself if you're not asking a question?
Sorry.
So then we have that's one way of looking, or we can have, for example, let's say we can say, okay, the entropy itself, for example, right, the entropy measure that you get, that itself should be, for example, let's say greater than some value. Only then I will continue getting more information from that. Otherwise, I'm okay with this entropy value if it is equal to some number, right? So these are some possible stopping conditions. Okay.
Did
Fine.
you
So
mean information gain by the fourth point? Did you mean information gain, parent entropy minus the?
sorry,
What did you?
information. No,
Did
no,
you
yeah,
mean?
no. Information gain. Yes, yes. So if the information gain, for example, is not enough, like it's it should be greater than some threshold, right? So then I would say, okay, go ahead and split the node. Otherwise, I would say there's no point, because the amount of information I'm getting, or amount of uncertainty and that I'm reducing is not worthy enough to continue the tree. So I'll just stop. That's another way of stopping.
How to
What is point 3?
how
Examples
to
less
have
than
the
threshold
threshold
node.
value?
I'm sorry, one by one. Bhushan, I guess you can ask. What are you
Yeah,
asking?
what have you said in point 3?
Yeah.
Example node less than threshold means what?
Yeah. So that is basically, let's say, if, in this example, when we're looking at the outlook variable. So now what I will say, okay, you go ahead and expand a node. I mean, look at the children of that node only if, for example, the number of samples, the number of rows that come under that node are more than some value, right? So let's say, if I had kept the threshold, for example, in this case to be 6, then I will not expand this node at all. I will not go ahead and check this this humidity, temperature, wind at all for this rain node. Why? Because the number of examples in this rain node are only 5. 3 positives, 2 negatives. Total 5 examples only I have. So I will, because I kept the threshold as 6, I will not continue.
Okay, that means
One way of-
the data set is too few for this particular attribute. You are not going further.
Correct, exactly. That's the thought process.
Excuse
Thank
me,
you.
that threshold, how we can fix?
So the threshold is not learned from anywhere. You cannot learn this from the data. These are all just some sort of hyperparameters which you try different values, and you see what works best for you, right? Yeah.
And
So
one
generally,
more question. I have seen one example in the net that the entropy value is more than 1, greater than 1.
okay.
Is it possible to have greater than 1?
Are they have they used what is the logarithm that they used? I mean, is it log base 2, log base
Log
e,
base 2.
log base 2, is it? Um,
I
I
have
don't.
seen only the tree and with the values of samples, input and entropy value,
Right.
in which the value of entropy is 1.54 like that, and when they come down, the 1.54 is reduced to point something. So is it possible to have?
So no, actually, I mean, I don't think so. Entropy, when you use log base 2, at least because the maximum possible entropy is when you have
One.
for binary sort of inputs is half and half, right? That's the maximum entropy system, because there's nothing known about the system. So that will be equal to 1. I mean, just check if it was information gain or entropy, and possibly it's possible that they made some mistake in the calculation itself. So just run the numbers and see if you're getting the right numbers.
Okay, thank you.
Many a times in the video and as well as the tutorial, there is a mention of the term hyperparameters.
Right.
I can understand features, I can understand parameters. So what is hyperparameters?
Right. Okay. Good question. So fine. So let's just take this right now. So parameter versus hyperparameter. So the most basic difference, I mean, how we distinguish these two things is this is something that can be learned from the data, right? So so here, for example, uh, for a decision tree, for example, the parameter could be which feature to
Feature set.
click on, right? That's one parameter, and that basically decides the number of nodes as a parameter of the decision tree and so on. So those are all the parameters of the algorithm, right? That you have, that is your decision tree algorithm. Hyperparameter is something that cannot be learned from the data, at least not reliably, right? Sometimes it is just that there is no way to learn. That's one possibility. The other possibility is it's not reliable for some for multiple reasons, right? So here in our previous example, I mean the example that we just discussed, these thresholds sort of things, right? Those are generally not learned from. I mean, it cannot be learned from the data at all, right? Because it's and if you there are some cases if you learn these hyperparameters from the data, what will end up happening is the model will start cheating to get the value to get the lowest training error, and that will end up showing as a very bad validation and test error. So generally we don't learn these hyperparameters from the data. So then the question is, okay, then what do I choose, right? How do I set a value for this, because these do affect my algorithm, right? Now for example, if here also what threshold I choose affects the way my decision tree is learned. So any thoughts on what could be used? This is something that we discussed last in the last live session also. So just if you want to take a guess on how do I then set these values, right?
One maybe could be trial and error and experience. Intuition, trial, error, and experience.
Correct. So trial and error. So then how do you if you remember last time we discussed splits of data, right? So what splits do we generally do for data in machine learning? Anyone want to give me all three names?
Training, testing, and validation.
Training,
When you
validation.
say testing, training, validation.
Yes, correct. So training, validation, and testing, three values. The three splits we do of the data, right? So when I say learn from the data, this is learn from the training data, right? And then what you do for these hyperparameters is you try multiple different values, right? For example, in the previous example, threshold, right? So what you will do, you'll set threshold equal to, let's say, 5, okay? And you will run your decision tree model on the training data, right? Now you will evaluate the training data on the validation set, right? And you will get some sort of a validation error, right? You will get some validation error, for example, let's say some number, right? So in the case of binary classification, you can see it as a misclassification rate or accuracy, whatever, inverse of accuracy, whatever, right? Then you will do, let's say threshold equal to 6, again train a different decision tree model, right? But that model will be different from the one that is learned at threshold equal to 5 because of the fact that that controls your stopping criteria, right? So it's possible that some node when you're having threshold equal to 5, that got expanded, but when threshold equal to 6, that node doesn't get expanded. So therefore you have learned two different rules from the data, two different programs from the data, right? So for threshold equal to 6, you will again do a training, and you will test that model, that whatever you got on the validation data and get a validation error, right? So now you will try a couple of these values, right? And how many values you should try, that nobody has a good answer, right? So so what we do is we generally try different values based upon how much computation power you have, etc. You try different values, and then whichever hyperparameter gave you the least validation error, you will choose that, right? So let's say, for example, let's say threshold equal to 5 gave you the error of 0.6. This gave, let's say, 0.2. So what you will do, I will set my threshold now to be equal to 6. Now that model that you had learned here, that will be used as a final model that you will run on your test data, right? And whatever error you get, that will be your test error. Fine. Is this clear?
Sir, can you repeat the last sentence?
Yeah. So what I was saying was that so we'll try a couple of these values. There is a couple of values for these hyperparameters, right? And based upon whichever value of this hyperparameter gave me the least validation error, right? So now in this case, I got a validation error of 0.2 for this threshold equal to 6. So I will choose that hyperparameter, right? So for me, that is the best that I have in my set of values. So whatever model was trained for this particular threshold equal to 6, right? That model will be chosen as a final model. And then whenever test data comes, you will apply that model on the test data and you'll run that in your usual process, make predictions, find out test errors, etc., etc. Yeah. Okay. I'm sorry.
Hello, sir.
Yeah, go ahead, Koneru.
Just one clarification between validation error and validation set and training set. For me it looks like they're similar, but there is a different motivation for each. Can you just elaborate on this?
Yeah, so we covered this quite a bit in the last video. So I'll just mention what the idea is. So training data is basically used to train your model, right? So this is basically again to motivate in terms of a student learning for an exam. This is basically all the question bank that you get, right? So somebody comes and gives you a question bank of all possible questions that can be gotten from a particular chapter, right? So you will give questions and answers. So the student can learn from this set of training examples. Now what we do is the validation is his examination. So on the particular day of examination, we ask questions to the student and we try to find out what is he right or wrong. That's the validation set. Okay, so we have a couple of questions which we give for the student to learn. We have a couple of questions which we use to test the student. Now, the idea why do we want these two separately is that the student can do very well on the questions that we gave to him by just memorizing. But we don't want that, right? We want the student to learn the concepts properly. Hence, we want a separate set called the validation set. So we'll see, okay, is it doing well on the validation set or not? Is the model doing well on the validation set or not? If it is doing well, that means it's learning the right concepts, the right patterns from the data. If it is not, it means it's just trying to memorize the training data, which is not good for us. Is that clear?
Okay, sir.
Right.
One question key in linear regression, can you have hyperparameters because they don't look likely?
Right. Yeah. Okay. So the regression that we have discussed in the class that doesn't have. So for example, let's say linear regression, we had, we saw y equal to some beta naught plus beta 1 x1 until beta p xp, right? So here we don't have any hyperparameters. So generally what we do is we don't just look at this sort of a combination. We also look at something like, for example, let's say if I have a single feature, I can do something called a polynomial regression, right? So let's say
order is the hyperparameter we give order of the equation, say x1 square x1 cube. So up till n, is that the hyperparameter?
No. So so that will come here in the linear regression. These are features, right? X1 to xp are different features. So that is not a hyperparameter, obviously, right? Because we know that the dimension of the data.
I'm talking about x1 ka how much degree.
Correct.
Is that a hyperparameter?
Yes, that's a hyperparameter. So I'm saying that in the class 1 example that you have, that is not any.
Yeah, linear pe to n order is 1.
Correct.
So that is not. I'm talking about n is equal to x. Then x is a hyperparameter.
Correct. Yes.
Yeah. Oh.
Yeah.
And for decision tree, will depth be a hyperparameter?
Yes, that will be because based upon how much depth we have gone, so we can choose to stop there, for example, as part of
and I got and for parameters in linear regression, beta 1, beta 0 is the parameter. These are the parameters. I want to know the delta between parameters versus hyperparameters. So beta 0, beta 1 till beta p are the parameters, model parameters. These are the parameters.
Right. Yeah. So in linear regression, so if you see in this particular formulation, there are no hyperparameters. There are only parameters. Parameters are beta 1, beta 1, beta naught, beta 1 until beta p. Right. Now there is something called as polynomial regression. That is, we look at not just a single power of the variable of interest, Rather, we look at multiple powers. So basically here I can say beta naught plus, let's say beta 1 x1 squared, beta 2 x, sorry, beta beta 1 x1, beta 2 x1 squared, beta 3 x1 cubed, right? And then let's say I can do this for multiple features. I can do it for xp also, right? I can keep on going until xp, or I can do some more things, some more complicated things. Let's, for example, let's say let's say
X1, X2.
right. So I can say alpha 1 to x1 x2, right? I can look at combination of them, right? And then I can say alpha 2 3 x2 x3 and so on. So now so here the point is that we say, okay, how many powers do you want to go to, right, of each single variable, and let's say how many combinations you want to choose. All of those are hyperparameters. So here the hyperparameters are basically what is the power of these variables that you want to explore. Max power, that is order of the polynomial, right? That is a parameter. Parameters are again beta naught, beta 1, beta 2, beta 3, alpha 1 2, alpha 2 3. All these are parameters. Here these are the parameters. No have a parameter because we have chosen the, in a way you can look at linear regression as a special case of polynomial regression where you have set the hyperparameter equal to 1. The power of variables to be maximum equal to 1. So obviously we cannot handle any interaction effects also. We cannot have x1 x2 because then the degree becomes 2 and all of that, right? So here the degree is set to 1, so hence I'll have only a single powers of all the variables. Yeah. Is that clear? Who asked that question actually? So Annapurna is asked in the chat, and yeah, so is it clear? Any other doubts here? Okay. Kanak, so I think that's answered, right? So is validation test part of training test? So no, we have three different sets of the data set we choose. Yeah. Okay. Okay. Yeah. So any other doubts, or shall we move on to the next concept? Right. Okay. Good enough. So okay. So now I was just planning to give you a flavor on, let's say, if I have multiple classes. Okay, so here, as we discussed, we were looking at entropy of the tennis variable always, right? Because this is exactly where we want to reduce the entropy. We want to get more information about this random variable, right? And so we looked at entropy of tennis variable at each root node, children node, and then saw, okay, how much difference, and that was our information gain. Now let's say instead of tennis yes or no, let's say I have a couple of them as maybe, right? Let's say this is also now maybe, right? And let's say maybe is a valid value of this tennis variable, right? So now the tennis variable is actually it takes three values. It takes yes, it takes maybe, and it takes no also, right? So in this case, how would you calculate the entropy of the tennis variable? Now leave all the information gain, all of the you leave. Question is, I have a random variable called tennis. How do I calculate the entropy of this? Any
By assigning, say, probabilities to maybe?
I'm sorry?
By assigning probabilities to maybe?
Right. And the probability will be?
Say 0.5 maybe. Yeah, हो भी सकता है, नहीं भी हो सकता है 0.5?
No. Okay. Uh, Not that maybe. Actually, just 1 second. I guess I'm using the right word here. Okay. No, so the idea here is the random variable can take these three values, right? It can take yes, maybe, or no. Now I want to know the entropy of this random variable. So I cannot assign a probability value for the value of the random variable, right? That is it won't be right, right? I want the probability that tennis as a random variable takes the value maybe.
2 by 14.
2 by 14, right? Hana, that's the idea. So 2 by 14. No is again, I guess, 5 by 14. That I haven't changed any of the no's here. So, and then yes would be 5 plus 2, 7, 7 by 14, right? So now we have what different values that tennis is taking in the data set that we have at hand and the respective probabilities, right? So now if I want to calculate the entropy of this random variable tennis, what will it be? Any thoughts?
How? Constant rather than with
We'll use the same formula, right? Minus
Right.
7 by 14 into log 7 by 14 minus 2 by 14 into log 2 by 14 minus 5 by 14 into log 5 by 14.
Right. That's it, right? So because again, the same thought process that I mentioned before, the idea is we look at all possible values of the random variable. That is how we define the entropy of any categorical variable, right? Let's say entropy of x. We're looking at all possible values that x can take. Then what is the probability of x taking that value into the log of that probability? That's it. With a negative sign in the beginning. Right. So here the probability that the tennis can take yes is 7 by 14 into that value. Then maybe is 2 by 14. So again into that value. No is 5 by 14. So into that value. That's it. Right. So between, let's say, if you have to apply the same thought process for a multi-class classification, it is the same thought process. Right. So just because the class, I mean it wasn't it was binary before, but now it is multi-class classification. So it is still the same sort of thought process that comes into picture. Okay. Any questions here? Otherwise, we'll move on to the next concept. Okay. Fine. Then let's what else do we have? Yeah, gene impurity is same thought process. So let's look at for continuous random variable, right? I mean, yeah. So let's say I have height prediction, for example, right? So I again have the same sort of data set, let's say. Okay. I'm trying to, get data on, let's say, oh God. Nice. So this is basically, let's say, father's height, let's say, son's height, sorry, mom's height, for example, right? Father's height, mom's height, and the son's height. So I'm trying to use these two variables to predict the sun's height. Now this is a continuous random variable, right? It can take any value, any continuous float value, right? So then, if this is the case, then how do we proceed? Any thoughts? How would you want to move ahead with this sort of a problem statement?
We can group them and then start solving the problem, sir, if it is
Group.
multi-valued attribute. Then we can group them into 2-3 categories and then find out the entropy for each one.
Right. Good. Yes. One approach is that, right? So I can basically group the sun's height, let's say, into 3 possible values. Some, let's say, less than 4, or then 4 to 6 and greater than 6, something like this, right? And then these three become 3 categories, and then I can apply the entropy formulation here, right? So let's say without grouping, if I had to do, how would I go about doing it? Let me just clear off a bit things here. So if I had to, same question, that is, I want to use, for example, let's say the sun side. I want to predict a continuous random variable, but without this grouping sort of a thing. How would I go about doing it? Any thoughts?
First, father height we have to take. Suppose, for example, less than 5 feet and more than 5 feet. From that, we have to get again divide the tree into mother's height. Suppose if both are above 5 feet means son's height is also above 5 feet, like that.
No, but the question, but the point is, how do I choose the random way? How do I choose a feature, right? So if I have to choose a feature, what we did before, we looked at entropy and we looked at information gain. Entropy of the root node subtracted from the average entropy of the children node, right? So what is a measure that I can use? Can I use entropy here, by the way? Any thoughts? If I don't do this, approach, can I use entropy here?
If you don't do that approach, then it will not be possible to do entropy.
Right, because entropy is for, I mean, the way we have been looking for is only for the categorical variables,
Yeah.
right? So what other measure do you think we can use to understand, well, like, is it, impure or not impure, right? Because we're trying to ascertain that only, right? Entropy is sort of impurity. So how much impure the data is, and we want to go more and more towards the pure this one. So what measure do you know of this?
That's Gini index. Some term. No.
So Gini index is also again for category variables, right? So anything you remember from linear regression classes? So in linear regression, at least in the way the class has been taught. So what is the uh, what is y? Is it continuous or categorical?
Continuous.
Continuous, right? And for this continuous, what measure did we use to did we use? MSE, right? So MSE can be used again as a same thought process. MSE can be used as a way to as a proxy of impurity of the node, right? Impurity of the node. This is the thought process. Okay. So what we will do is, again, so see, in decision tree, for the attributes for the features, you still have to do this sort of business, right? Because I mean, we want to take decisions. We want to do something less than, more than, those sort of things. So one example that ma'am gave, like, choosing a threshold and looking at this father's height less than something, father's height more than something, and so on. So let's say we chose some threshold, right? Father's height, let's say more than 5, less than 5, right? Now, to find out the, so first what we will need to do, we need to find out the entropy at the root node, and then entropy of this child, again this child, and take the average, subtract from this, same thought process, right? So the way you want to choose between features is basically you want to look at how much the impurity is reducing. That's the idea. Now, the way to measure impurity for a continuous random variable, we have chosen it to be MSE, right? So what we can do is I can look at the MSE value for when I choose this particular node. So for this children node, and then for the root node, right? Now, okay. So then, how do you go about calculating the MSE? Can we do it in the same way we did in the linear regression problem statement? Any thoughts on that? So how many of you remember what I mean? No, in linear regression, what we did MSE of? Let's say that's the question.
It was the training point. I mean, the point which is on, and it is finding it. How near is a point to the line? So
True minus predicted.
True
yes,
minus predicted. Simple, right? True minus predicted. So if you say y is true, predicted is let's say f of x, right? Okay, predicted is f of x, and we did square of this, right? And let's say we'll do this for every element, and then we took some mean, whatever, right? And all of that we did. Okay, all that is fine. Here, do I have any? So in this particular example, can I do the same thing here? Is there something missing? How do I get the MSC? Let's say I want the MSC for this node, right? So how do I get the MSC now? So do I have the true values though? Do I have the true values?
True values you have, but you don't have predicted values.
Right. That's the issue. I don't have the predicted values. So what we do generally in decision tree regression, so we're trying to do regression using decision trees. So we take the mean value of this particular, values in this node, that as the prediction from this node, right? So the mean of the continuous random variable, whatever we had, let's say mean of the height in our case, right? Yeah, so mean of the height that becomes our prediction of this node, f of node, let's say, right? So then what we do, we look at this yi, there is a true values minus the mean of this node, and then calculate the MSE, right? So the same way I can do for the whole data set also, right? So I just take the mean over the data set, right? So let's say all the values I have here, I take the mean of them, I calculate the MSE by doing each target the true variables minus the mean over the whole data set. Again, same, squared it, whatever, you'll get some MSE value. Same thing you will do for this, but here you'll take the mean of only the rows which belong to this particular node, right? That is basically for all the rows where father's height was more than 5. You'll get the mean, you'll get the MSE, and you'll keep it. Same thing you do here. Then the same question, that is what is the gain, or what is the decrease in impurity in some sense, right? Or delta MSE. So you'll say MSE uh, of the parent, right? That's a root node in this case, minus the average of the children. Average, again, you will do a weighted average. The weights will be how many samples I have in this particular node, how many samples do I have in this particular, that's it, right? So this average is basically number of samples. So number of samples divided by total samples in that node of the child node, for example, into the MSE. Take the summation over all possible nodes, right? Okay, is this clear? So this is how you can use the same decision tree algorithm, but for regression. So now the prediction, when you want to do the prediction, is again, as we discussed, just the mean of the node, right? So at the leaf, when you go, for example, you choose to stop at possibly now I have only 2 features, so you have to stop after depth 2 in this ID3 algorithm, right? So when you stop after this depth 2, so what you predict from that node is the mean of the values that are present in that node. Okay. Is this fine? Is this clear? Any other doubts here?
What is this here written? Sigma AS node. What is this?
No, not A, sorry. That's the number, symbol for number.
Okay.
Hashtag. So number of samples of this node, right? That belong to this node divided by total number of samples, summation over all possible nodes of that is children. This.
That is into MSE.
Yeah. So each same thing what we did before, right? Average of children. So each child nodes ka MSE with the fraction that number of samples belong to which are there in that child node. That's it. This is the average.
Okay, and once again, MSE, how we calculated? We calculated by taking the average of the node.
Correct.
Minus the value of the node.
Right. So basically, I will have, let's say, some 10 examples in this node, right? So I have 10 y values, the true values, right? So each of these 10 y values, the true values, I'll subtract with the mean of these y values. That's it in that node.
Okay. There isn't any example in our slides or even in the homework on this.
No, there isn't. But in the tutorial here, he has done the decision tree regression. Hence,
Okay.
I thought that you should be aware of what happens
Okay.
in decision tree regression as such.
Okay.
So yeah.
But
So
is decision tree really used in regression, or it is very rare?
No, it is used in both the problem statements, classification and regression.
Okay. And just a question, broad question. Regression does classification as well as if you use something like sigmoid function or something, you can do classification. Okay, and but you don't call that regression, or regression is totally separate from classification. Regression has to be continuous, and classification has to be discrete.
Yes, that is true. So we make that difference between these two classes of problems in supervised machine learning based on the fact of what we want to predict. So is the predicted variable is it continuous, or is it discrete in some sense? It can be ordinal also, but is it discrete in some sense? So if it is discrete, it's termed to be classification. If it is continuous, we term it to be regression. So
and decision tree is an algorithm which we can use for regression as well as classification.
Correct. That's true.
That will be correct? Or correct to say that?
Yes,
Okay.
yes, correct. Yes.
Okay, thank you.
Yeah. There's an algorithm. What we have covered in the syllabus is basically called the ID3 algorithm for building a decision tree. There's also something called as CART, C-A-R-T. So I think the full form itself is classification and regression trees. So the idea is that and from that only we get this idea of how we can use a decision tree for regression sort of problems. So the idea is the claim is that this tree method can be used for both regression as well as classification problems. And going forward, we'll see. I think in the next lecture we'll have this the one that you mentioned using sigmoid, the logistic regression, right? So, but that is used for classification. But the NYC called logistic regression, hopefully they will cover. Otherwise, I'll mention it in the class, right? That's one. And then we'll also look at something called as random forest. That is a very well-known algorithm for regression as well as classification, which builds on decision trees.
Okay. And one last question. Which is better, regression through decision trees or pure regression? Or is there any case where you preferred regression using decision trees or just pure regression?
See, both linear regression and decision trees for regression both enjoy a lot of similar advantages because both are in some sense interpretable. You can understand which feature is causing most importance in your data set and all of that. But typically, yes, if you want to choose between decision tree for regression and linear regression is generally preferred for regression problems as a first approximation, because the fact that it is, let's say, famous and all of that. I mean, it is the first algorithm that anybody goes through for in an ML course.
Okay, thanks.
Sir, just one question. See, when we use decision trees for regression, I feel the bias will be more, right, than using linear regression. For example, if you use the traditional regression problem with continuous variables, label variables, if you use a decision tree, it is likely to have a more bias. Am my statement making sense?
Uh,
Because the decision trees are considered as actually having a high bias.
Okay, I mean, you're right in that sense. And see, but but the point is the comparison is not fair in that sense, because linear regression, you're saying I will use only all the variables, and that too only in their one-th power, right? And the degree of the polynomials that we discussed today, only in the one-th power. That sort of simplistic approximation doesn't exist in decision trees. So in that sense, linear regression is always a simpler model. So if it's a simpler model, then bias is low. So that is the reasoning why you would see low bias in linear regression. Now, when I use polynomial regression, that's sort of, in a way, I would say more comparable to decision trees. There again, it's a flip game. I mean, you can have high bias even in the polynomial regression system.
Sir,
Okay.
none of the, excuse me, sir. Sir, none of the algorithms can have an assertion, right, sir? This will definitely generalize well.
No.
No. Okay.
No. Yeah. We cannot make that claim in any of the algorithms, actually, even in whatever complex algorithm that you will learn going forward also. That cannot be done. Hence, we use a validation set to make that, to at least understand in some sense, to a first approximation how the model is doing. But that's it. There's no guarantee.
One question about bias and variance. I think you may have covered it last time. First question is, does bias have any measure? Like variance could be variance and variance could be standard deviation. At least you get some sense of what is variance. Bias looks more like a qualitative term. So is there any measure? That's first question. Second question after this I'll ask.
Yeah, so there is a proper way to measure bias. I mean, we have a mathematical formulation for all of that. I thought to cover in this uh, session, but seeing all the questions on decision trees, I thought better to cover the syllabus first. Um, so let's do one thing. In the next class, let's do proper the bias variance decomposition, and we'll see what is exactly meant by bias, what is meant by variance, and you might be surprised that it's generally not possible to also quantify a lot of things there. And then we'll see, all those claims that have been made before. If you increase training data, how does it help? Complex model, simple model, all of those, things will do that. So let me make a note. Next class we'll do the bias variance composition. So we'll understand what each terms are and how they work. Or I can ask the next TAs also. So let me ask the guys who have it on Monday and Tuesday. If they're willing to cover, then we can do it there itself.
Sir,
Okay, thank you, because it is very important. Otherwise, we are getting confused. You know that about the things which are overfit means you have more bias, but on training data, but on test data, there is more variance. So ये सब confusion होता है.
Right. Yeah. No, I
Sir, let me state my intuitive understanding of what bias is. For example, let us say you have a training data set with four feature variables, and one outcome variable. Okay. So if you fit a polynomial of fourth degree, so all the data points will perfectly fit with no training error. Okay. Absolutely no training error. That is possible because you have a chance to take a higher degree polynomials. Fourth degree, four variables, fourth degree, five variables, fifth degree. So 100% will fit. But the problem is that is only on the training data. But unknown data comes, it may not be true. So what we think is that whatever data we have, it is not perfect. So don't try to do a perfect fit. So there will be some error in the given training data itself. Accommodate that error, then and accordingly don't try to force fit with a high bias. So leave some tolerance so that an unseen data will not be that far away from what you. So this is what my intuitive understanding.
Correct. Yes. And the point that you raised was very good. That is, even in the training data, you can have some noise. Now that is exactly where you start getting, things, this bias variance starts moving out. So there's a very clean mathematical proof to, distinguish these three terms. So we'll take it up in the next, but your point is right, and we'll take it up in the next session, or in the Monday Tuesday sessions. Yeah. Any other questions?
I had a question, like the previous guy said there were 4 feature variables. So with fourth degree, we will be able to completely fit, but uh, it's not feature variables, it's examples. 4 examples, then fourth degree will completely fit. It's not x1, x2, x3, but the rows, then it will fit properly. The correlation is between number of examples and nth degree polynomial, but it's not with respect to features.
Yeah, you're right. You're right. Sorry. Yeah, correct. So it will fit the whole training data properly because I have so many, let's say, whatever,
If n examples, then with
examples.
n then n minus 1th degree, it will fit. It's not features. Anyway, features के साथ कोई relation नहीं.
Correct. Yeah. True, Abhirup. That's correct.
And in decision tree for binary classification, we can go for log to the base 2. If it is more than 2 classification, can we go with the log to the base 10?
So again, I would say, use any, base for that matter. The point is what feature you will use to, let's say, split. That will be the same because everything gets scaled appropriately, right? So at least in the examples that you have in your assignment, all of them are binary classification. Just so for now, just go with log base 2 and you should be fine.
But as you mentioned, when I use log to the base 10, I am getting entropy value more than 1, greater than 1.
Right.
Okay.
See, entropy again. Entropy is the measure of the log, this one. So because if you change the base, again the entropy value will also change. The max value will also change. So if you think about it, we just discussed this formula here, right? Yeah, this one, right? I have sigma x px log x. Now, if I have log base 2, the maximum value will be dependent on that base. And then if I use log base c, again the max value will depend on that particular base, all of that. But the point is this, because you're taking, let's say, subtracting, two entropies. One is entropy and then one is the average entropy of the children, right? So what will end up happening is all of your values will have that same sort of multiplicative factor. So hence any decision that you take of choosing a feature or not will still remain the same regardless of whatever base you choose. That being said, for the sake of your assignment, make sure you use log base 2.
Yes. Sir, but in all the discussions related to entropy, by default, we should be using only log base 2, nothing else. But that is the basic definition of entropy, right?
Again,
sometimes in the examinations, by mistake, we use normal decimal rather than log base 10. But I realized this mistake. But whenever in the entropy calculations, always by default,
okay.
actually, in fact, calculators also they have log base 2, log 2 calculations are there. Yeah.
I will agree. So let me make a small clarification. If I say that the weight of this particular object is 1 kilogram versus I say the weight is 1,000 grams, is it different?
No. Let's say.
That's it. So that's the argument that I have, because when you say log base 2, you're calculating in the units of bits. If I take log base e, for example, you can take it in the units of nats. So whatever value you get, let's say when you say entropy is 1, It's not just a value, it's actually a unit associated with it. The unit is dimensionless. That's will not go there, but the entropy, the max entropy when you use log, when you take base 2 is 1 bit. That's what we're saying, trying to say.
Yes.
When I say log base, if I use, for example, let's say log, base e, I say nat. That's the thing. That's it. Okay. Any other questions? Theory or otherwise, anything is fine. I mean, any questions? We can take that. Link to the recording, is it? Just give me a moment. So just so that it is there here. Yeah. So this is the playlist, YouTube playlist, which I will be updating after every session. So you can just make sure you see there, in case you miss any part. What else questions do we have? So yeah, somebody asked this. Can you explain the least minimum slope method for finding expected values of sum of squared error? Okay, so Sandeep, what? Is there anything specific that you want to know from that particular problem statement? Is he here? So go ahead and ask. Otherwise, if you want a recap of the method, we can get it done in Monday, Tuesday classes, because Wednesday you have to submit your assignment, right? So we can get that done, not a problem. Yeah, Bhushan, go ahead.
Yeah, what I wanted to ask was nothing directly with regard to the resources. We have got tests, rather assignments to be submitted. Are there, other than these assignments, any resource to practice, like practice problems which you have at the end of, when you attend a class or a textbook, something? Is it available? And even are the last couple of years test papers available? Assignment or something available?
Yeah, the last couple of this one, I'll get back to you. I mean, the NPTEL guys have to get back to me. I'll get that clarified. Mostly by Monday, I'll get that clarified. I'll put it on the discussion group, right?
Okay.
Whatever the answer is. But I mean, so how many of you feel like you need some more examples to, be able to solve your assignments confidently? Okay. Okay. We'll get that then. Sure. Yeah.
It'll only make you feel more confident. You get more practice. That's all.
Sure. Yeah. Makes sense.
दिमाग में जल्दी जाएगा वो.
Sure. Yeah. Okay. Fine. I'll check that and get back to you. Saurabh, I guess that your question was clear, I guess. So after calculating information gain, how do we choose the next attribute? Same thing that we discussed, right? So whichever attribute has the least information, highest information gain, that's the attribute that you will choose, right, for splitting. And then you perform the split. That is, you make the children, all of that, repeat the procedure. That's it, right? Any other question?
Sir, one question.
Yeah.
If the number of training examples, let us say, is less than the number of feature variables, is there any way we can fit actually? We can't fit, right? We can't model anything because The number of examples are less than the number of feature variables.
Right. Yeah. So you can't fit anything reliably. That I would say. I would not say not be able to fit.
There's
Uh,
no relation with that actually. There is you're talking about feature set number with instance number. There is no relation absolutely.
I'm talking if it is equal, then it becomes a linear
There is no
equation, perfect
relation.
fit.
You're taking feature set and you're talking about number of samples. If you're talking about nth degree polynomial, then you can say something. It has no relation, means with feature set, number of features and number of points you're taking, it has no relation with that. So if you're telling you're approximating with some nth degree polynomial, you can say something about that, how much well it will fit or not fit.
No, I'm talking about linear regression, not polynomial, just a pure linear regression. If we have
so if you have say 100 x1 x2 karke x9 110 and you have say 95 points, you can very well try to get it right, because you need it has no relation basically, what I felt. Raj can confirm.
right. So okay. So let's say that your value, whatever output you had, that actually depends on only the first three variables. Let's say, okay. And so then, if you are able to reliably estimate the first three parameters, you're done, right? It doesn't matter, how many features you have, how many samples you have. So that's the thing. But generally speaking, if you have a lot of features, you need more data to reliably estimate all the parameters. And we will see that when we come to bias based decomposition. So that will basically bring out the point that if you have a complex model, you need enough data to have less variance in your estimate. That's it. That's the one line answer.
One terminology question. The professor, Mrs. Sarkar, uses many a times the word instance. What is the actual meaning of the word instance? It is a set of one particular set of examples, like if there are features F1, F2, F3, then the values of those features plus the target function values. Is that an instance?
Yes, as Abhirup was saying, it's one row. So it's the set of
one row.
So the values of the features and the value of the target variable. That whole row is called one instance of the training of the data that you have at hand.
Okay. And therefore, when you are going to predict, you will not have the target function, but that also it comes under the terminology instance.
Correct.
So
y and x bar vector pura. That is one instance. You can take it like that. Means if you use it for training purpose, you have to take that y also.
Right. So when you say instance, it's involving with the y, and so again, so we're trying to predict, obviously, because the target variable will not be a part of your input features. So then what you say, you say I will use the instance of the input data. Instance of input data, just the features, and you pass to your prediction function, you get the output. That's when you use that corresponding value of your target for that instance of data features that you have. You will use the corresponding value for your target, calculate the error, MSE, whatever you want, or whatever things we have. That is how you do your error calculation, etc., etc. Yeah.
Sir, instance space and feature space are same, right, sir? It is the same. It means the same. The feature space and the instance space means the same, right, sir?
So
I mean,
again,
one is instance space is a bigger, so we apply basically bias to reduce, and that becomes the feature space.
That instance you're talking about. No, 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 no. See, feature space is basically all your possible values of the features, right?
Yes.
Instance, because we're saying that it's also contains the feature value in it. It's the joint space. The features as well as your uh, target variable, right? So it's always one dimension. I mean, if you have a univariate target, then you have that also as part of your total space that you have to explore in sense of finding the right functions.
Okay, sir. Input and output together is instance, and only input
Yes.
will be feature space.
Yes,
Correct.
correct.
Oh, thank you.
N plus 1 degree view, there is only one target. N plus 1 degree is instance space. N degree is instance space.
Yes.
Sorry, N plus 1 is the instance space and feature space is N degree. If N is the dimension of the N features you are using. And there is one vector.
I would not use degree, dimension.
Dimension.
N
Correct.
dimension.
Not degree. Degree is completely different. Dimensions.
The other way we can imagine the instances is that if we have, let us say, n features, you imagine n-dimensional space, and in that n-dimensional space, all the instances, points, will be positioned in the n-dimensional space.
N plus 1th dimension space, that instance will be there.
N plus 1. Okay.
Yeah.
Yeah.
Yes. Yes.
And when you predict, because the prediction is not there, the instance space would be just the feature space.
Correct. So when you're trying to predict, you can only use the
It's for unseen data. For unseen data.
Yeah, for unseen data.
Whatever prediction is always on the n on your features. Features you'll pass it as input to your model. It'll do some prediction. The prediction lies in that one remaining space. That's why you can do a subtraction or whatever. I mean the MSE sort of things, right? So your features is your n-dimensional space that goes into your prediction function. It outputs a single value in case your target is a single value, and that is then compared with the target, the true value in that space, in the one dimensional space, right?
So this is a question for all. Is there a WhatsApp group pertaining to this course?
No, sir.
Or can we form one?
No, I think we are supposed to use NPTEL discussion forums only, because the same question was asked in one of the other NPTEL course. So the committee, the NPTEL people said that you are supposed to use discussion forums for discussion. Yeah.
Okay.
Yeah, so I mean, supposed to is fine. The reasoning being that if you ask questions on that, because all the teacher, the course TAs, PMRF TAs, even all of your other people who have joined the course will have access to it. When you want to create WhatsApp groups and all, it becomes an issue because you might not cover everybody. So it's just that the quality of the response may not be good enough. That's the thought process. Yeah. Okay. Anything else? Otherwise, we'll close the meeting for today.
So the recordings of all the lectures will be available on the same link. If in case we are unable to attend the live meeting, so
which link? Yeah. So I've shared a YouTube link, right? So that will have all the recordings of my sessions that I'm taking. So every Saturday session will be added here. The previous sessions has already been added, and this I will add today or by tomorrow EOD. So by Sunday EOD maximum, you can expect that my sessions will be up.
Hello.
Yes, go ahead.
You mean this is the link for your lectures only?
Yes, because so each of the PMRFTs are supposed to keep their sessions in a separate YouTube playlist. That's the mandate from the NPTEL PMRF committee. So this is for me, and hasn't so I thought NPTEL has already shared no
No, I
some.
couldn't find. I searched in the announcement also
Sure.
because last time also I couldn't attend the entire lecture. I missed in the beginning part of the lecture. So I just wanted to go through the recordings. So I tried to search for the link. So I
Okay.
think that it is supposed I mean one lecture per week, no? One additional this live lecture per week it is.
Yeah. I'll do one thing. Let me email them once, and get the ball rolling. Let them share the links also with you guys. Yeah. We
So am
can.
I right? So it is, I mean, the plan is like one live lecture per week, right?
Yes, one live lecture per week by 1 p.m. TA. So so every week you'll have three sessions, three live
Oh,
lectures. One on Saturday, one on Monday, one on Tuesday. The timings again are there. It's there in the announcement page. I guess that's.
okay.
Yeah.
Yeah. Thank you, sir.
Yeah. Any other questions? Entropy calculation, which you showed, which year assignment? No, it was not on an assignment. I've just done that using the example mentioned in the video also. So, ma'am, I guess she mentions this, and she shows the full tree that comes out of it. So I've just showed how you can proceed in multiple different scenarios. So it was not from any assignment as such. Vara power. So, could you please explain the formula for finding the value of the coefficients in case of linear regression? You can skip it. So, we didn't do linear regression today. So let me get the regression. I'll tell the other TAs if they can take it up, right? Uh, uh, so linear regression, yeah. So we'll get that done, and bias variance decomposition. So I'll try to get these two done by the others. Otherwise, we'll do it in the next session.
I think just to inform, I just went to that NPTEL site of our class, and this live recording of last tutorial. I mean, this lecture one is there.
Okay. So then, yeah, please, let people know. So you can, go ahead and do that then. Who was it?
Yeah, if you go to this problem solving session recording, there is a tab, and click here. You get, I think, week one. You get it. But it is put on Google Drive. I don't know what it is. And YouTube. It's on YouTube link last time.
So there you go. I mean, so they've already done that. So please go ahead and you can watch that.
Yeah. Just to inform.
Right. Thanks for that. Anything else? Otherwise, any last minute questions? No? Okay. Okay, then we'll meet next Saturday. So next Saturday we'll probably try to do the assignment questions that were done, which you will have as a deadline in August 9th, right? So just let me know either through discussion forum, just if there's anything that you want specifically to be done, or we'll do any one of the concepts in detail in this lecture. Yeah.
Sir, even assignment one question is not yet sent, sir. Answer.
Yes, but the assignment one deadline has been moved to 9th August again, right? So that was a problem. So hence I discuss that. So then I guess hopefully next Saturday we'll have both the assignments done by that time. So I can discuss both of them, and we'll finish it.
Okay.
Yeah.
Sir. Okay, sir. Thank you, sir.
Fine. Okay. Fine then. We'll meet next Saturday. Yeah.
Okay. Thank you, everybody.
Thanks.